So, consider a 2D central force setup described by the Lagrangian m/2 r dot squared plus r squared theta dot squared minus vr. Okay, so we've got two conjugate momenta here, r and theta. We have dl by dr dot and dl by d theta dot. That gives us mr dot and mr squared theta dot. And we can rearrange to get r dot equaling pr over m and theta dot equaling p theta over mr squared. Okay? We derived this Lagrangian in the last video where we looked at the Lagrangian for a particle in circular motion in polar coordinates. So we're going to work out the Hamiltonian. The Hamiltonian is going to equal the sum of pi q dot I, okay, and then we minus your Lagrangian, and we're summing over I. Okay, we should know that by now. So what's this going to equal? So we're going to sum over I. So we have I is going to be theta and r, because we're summing over our two variables. So therefore we're going to get PR times r dot plus p theta times theta dot, okay, for that. And then we minus the Lagrangian, which we have up here. So we do m/2 r dot squared plus r squared theta dot squared, and then we minus VR, like so. Okay? Brilliant. So this is going to equal, as you can see, PR multiplied by PR over M, because that's what R dot is equal to. So we do PR over M, okay, and then we add P theta multiplied by P theta divided by MR squared, okay, and then to that we minus M/2 multiplied by PR over M all squared, okay, we're just substituting R dot for PR over M, and then to that we minus MR squared divided by 2 multiplied by P theta divided by MR squared all squared, and then we add VR, okay, because the minus and the minus make it a plus. Okay, so that's our Hamiltonian, so we can obviously simplify this down a bit. Okay, when we do so, we can see this will give us PR squared divided by 2m, and to that we add P theta squared divided by 2mr squared, and then we add VR at the end. Okay, and that is our Hamiltonian. So, now we've computed the Hamiltonian, we can look at the Hamilton's equations. Okay, so I'll write down the Hamiltonian once more. What did we have? We had H is equaling PR squared divided by 2m, and then we add P theta squared divided by 2m r squared, and then we add our potential energy, which is VR, like so. Okay, so the four Hamilton's equations are r dot is equaling dH by dPr, okay, this of course will give us r dot equaling PR over M, okay. We also have PR dot, which will give us, of course, as we know, dH by dr, okay, dH by dr. Rearranging, we get PR dot equaling p theta squared, okay, divided by mr cubed, and of course we minus v prime of r. Just take the derivative of our potential energy. Alright. We also have theta dot. This will give us dh by dp theta. Okay. We can rearrange to get theta dot equaling p theta divided by mr squared, like so. And then finally, our final Hamilton equation, okay, for our polar coordinates, we have p theta dot equaling minus dh by d theta, okay, and this is going to give you p theta dot equaling 0. In other words, this is the conservation of angular momentum, which I wanted you to derive in the last video. Okay, so there you have it. We've worked out the Hamiltonian for our Lagrangian, and we computed the Hamilton equations. So I'll see you in the next video.